Good morning, everyone. So today we'll discuss one experiment, that is determination of voltage regulation by zero power factor method in an alternator. So in this experiment, we need to discuss some terms related. That is, first one is voltage regulation, second one is zero power factor, third one is load to get zero power factor, fourth one is open circuit characteristics between field current and no load voltage E. Next is Z.P.F curve, then Pottier triangle, then the field current required to overcome the demagnetizing effect of armature reaction, that is Ia into XAR drop, and next the second field current which is responsible to overcome the armature leakage reactance drop, that is Ia into XL. These are the two drops that will be experienced during the voltage regulation process. So one by one we'll start to discuss. Next, it is voltage regulation. So as we know that voltage regulation means what? The regulation of voltage from no load condition to full load condition. So it is calculated by the percentage of voltage regulation, and it is equal to no load voltage minus full load voltage divided by full load voltage into 100. So in this mean process, what we are observing, that full load voltage will experience a drop of voltage. So that drop of voltage is due to some parameters, that is, it may be due to the armature reaction drop, it may be due to the leakage reactance drop whenever a load is connected. So gradually we will discuss one after another. Next is zero power factor. As the name specified, we have to determine a zero power factor. So power factor, as we know, it is cos phi. So cos phi is equal to 0. So what about the phi? It is 90 degree. So phi is the angle between voltage and current. It is the phase angle between voltage and current. So here one question is arise. So how can I determine a zero power factor? So zero power factor means if the phase angle between voltage and current is 90 degree, then only we can get zero power factor. Then here one question is arise, how can we get a zero power factor? So zero power factor can be achieved by different type of loading conditions. So as I have already told, there are two types of loading conditions are there for which we are getting a zero power factor. Number one, it is either we are using a purely inductive load or purely capacitive load. So these are the two loading conditions in which we are getting a zero power factor. So in this experiment, we are using purely or highly inductive load to conduct the experiment. Then we'll study OCC and how we'll draw the OCC curve. As the name specified, OCC stands for Open Circuit Characteristics Curve. So in the diagram, we can explain how OCC curve will be drawn. So look at the diagram. Here we have two circuits. One is a field circuit and second one is the armature circuit. The field circuit contains field winding. The armature circuit contains three-phase armature winding. And as it is open circuit characteristics, so here the secondary side or load side or armature circuit is open circuited. So this is open circuited. One voltmeter is connected across the winding in parallel to measure the open circuit voltage E0, and one ammeter is connected in series with the field winding in the field circuit to measure the field current, change of field current. As it is an experiment, we need to change the field current, and accordingly, So in OCC curve, we need to change the field current by means of the resistance connected in series with the field winding. It is a changeable resistance by means of which we have to change the field current, and accordingly we'll observe the value of induced EMF over this voltmeter, and the curve in between the field current and open circuit EMF will be rise at this point. So this is called as OCC, open circuit characteristics curve. Next, right. Then after knowing the open circuit characteristics curve, we will discuss how to draw Z.P.F curve or zero power factor curve. So in this diagram, what we are getting, that is OCC line we are getting here. The red mark will symbolize the OCC curve. Then in second case, we need to draw Z.P.F curve. So for Z.P.F curve, we need to find out 2 points. One is point C and second one is point S. Then what is point C? So as you can observe here, the point C is called as the point where we are having a field current but we don't having a terminal voltage. That means what? It is observed at short circuit condition. So the point C is the field current at which we are getting a rated short circuit armature current. Then what about the point S? The at point S we are having the value of field current and we are having the value of terminal voltage. So the point S is that point at which we are having a field current such that we are getting a terminal voltage, that is full load terminal voltage, and a current, that is full load armature current. So these are the 2 points we require to draw this Z.P.F curve. So I will draw the Z.P.F curve in parallel with OCC and what we are getting here. Then next step, we have to draw a line which is parallel to this OC line. OC means it's the field current line. So we have to draw a line from the point S up to Q. So S and Q is the parallel line with respect to OC, and this is the line we need to draw. Then at point Q, I need to draw a line parallel to the air gap line like this. So this is QP. QP is the line. QP is the line which is parallel to the air gap line. So the P is the point which is touching the OCC curve. So QP is the line parallel to the air gap line and P is the point touching the OCC curve. From the point P, I will draw a perpendicular to QS. From the point P, I will draw a perpendicular to QS. So this perpendicular will touch QS at the point R. So here one perpendicular triangle is developed, that is P, R and S. P, R and S as the right angle triangle, which is called as Pottier triangle. So from this Pottier triangle, we can easily calculate the field current required to overcome the drops regarding the voltage regulation process. Then what are the drops we need to calculate? This is the drop. Here IF2 or KL. This KL represent IF2. It is the value of field current required to overcome the demagnetizing effect when a load is connected. Then next current is this one, QR. So look at the point QR. QR is the value of field current which is required to balance the leakage reactance drop IA into XL whenever load is connected. So these are the two drops which affects the voltage regulation process, and these are the field currents, that is RS and QR. These are the field currents required to balance the demagnetizing effects and leakage reactance drop whenever load is connected during voltage regulation process. Now we'll discuss the phasor diagram to represent the voltage regulation. So in this phasor diagram, first look at the reference we are considering. Here in the x-axis we are taking the voltage V. So V stands for the terminal voltage of an alternator. Then another phasor is IA. Current phasor is IA. This is armature current. So this armature current is lagging behind V at an angle of phi. So as armature is having some inductive coil, therefore current starts to lag behind the voltage by an angle phi. Then at the point K, I will extend one resistive drop, that is Ia into Ra. It is the resistive drop due to armature resistance across the armature. So this IaRa drop will parallel to the current line, current phasor Ia. So as it is a resistive drop, it is parallel with the current or in phase with the current, corresponding current, that is Ia. Then at point L, another phasor is drawn. So this is the phasor that will represent Ia into XL. So Ia into XL is a voltage drop due to leakage reactance XL. So Ia into XL is a voltage drop due to leakage reactance XL. So as it is a reactive voltage drop, therefore this voltage drop will lead the current by an angle of 90 degree. So therefore it is 90-degree reflecting here. Then after this reactive leakage reactance drop, another drop is happening across the armature due to the armature reaction drop, that is Ia into XAR. It is again the same type of reactive drop, therefore it is also perpendicular with the current or phasor, that is Ia. So finally, if we will add all the voltage and voltage drops like V, IaRa, IaXL and IaXAR, then it will give the total voltage, that is E0. E0 stands for no load voltage. So no load voltage can be equals to the terminal voltage V plus armature resistance drop Ia into Ra plus armature leakage reactance drop Ia into XL plus armature reaction drop Ia into XAR. So that will give rise E0. Then you can see here an intermediate phasor is representing OM. OM, it is representing E. E is the voltage. E is the voltage excluding the armature reaction drop across the armature. So E is the voltage excluding the armature reaction drop across the armature. So for which we have to represent the field currents. So you can see here we have field currents phasor, that is IF1. So this IF1 is nothing but the field current which is responsible to produce the voltage E across the armature. Therefore, we are representing this IF1 at an angle of 90 degree with respect to the voltage phasor E. Then second field current phasor is IF2. So here IF2 represent the field current which is responsible to overcome the leakage, the armature reaction drop, that is Ia into XAR. So this IF2 is perpendicular with the voltage drop Ia into XAR. So finally, we will get a field current, that is IF, as a phasor sum of IF1 and IF2. IF1 is the field current responsible to produce the voltage E across the armature terminals. IF2 is the phasor represent the field current which is responsible to overcome the armature reaction voltage drop, that is IF2.